Hello everyone, my name is Godfrey, working as Assistant Professor in the Department of Mechanical Engineering, Maharaja Institute of Technology, Mysore. I am here right now to discuss with you regarding a subject called as Computer Aided Engineering Drawing with a subject code as prescribed by the Visvesvaraya Technological University as BCEDK 103/203, depending upon whether it is offered in first semester or second semester. Now before I start with the today's discussion, I would like to remind you that one of my colleague, Professor Harish, has already covered a few of the topics regarding the introduction, but still we will just go through a bit of revision of the same thing. Now we are aware that as engineers that we have been using a language called as drawing since one can remember. Basically what drawing refers to is the fact that it is a mode of communication. Basically drawing is a mode of communication. Set apart just a drawing that you might have done at home, in the schools, leading up to biology or whatever it is. Drawing is basically a mode of communication wherein we are trying to communicate certain information through a picture. So it is without using any kind of words, we will be able to communicate, and that communication basically is like a drawing speaks more than 1,000 words. With that particular preamble, basically a drawing is a graphical representation of an object. So graphic language is a language that has been used since the historical perspective, since the historical times, wherein symbols were used, different kinds of animal pictures were used. Lots of languages basically have been derived from the earlier days or the ancient days, wherein the pictures and symbols were basically used. Now drawing is a graphical form of representation of an object. Regardless of whether we are dealing with the two-dimensional object or a three-dimensional object, we can make a picture. We can make a picture of a mountain sitting here in a classroom on a two-dimensional sheet of paper. Anything that we basically have in the form of imagination or something that we have in your mind, even those things can also be put across on a two-dimensional sheet of paper, wherein we'll be able to communicate to ourselves as well as to the person who is actually looking at the drawing. We'll be able to communicate a lot of information without using any kind of verbal words. Now the problem that we have with the drawing is most of the times it does not give us the true information. It gives you some sort of a pictorial representation of an object, wherein we will be able to perceive the shape of the object, not necessarily the size of an object. So basically with only the partial information, if we try to take it further for any kind of analysis, we'll be making a lot of mistake, because the drawing as it is not giving you the true information. But now engineering drawing comes into the picture, wherein if all the information regarding the shape of the object, size of the object, the material specification, constructional features, etc., and you name anything, if all the details are added into that particular drawing, it becomes an engineering drawing. And engineering drawing is the one that we will be able to perceive, or anybody who has the capability of reading a drawing. There will not be any variation from one person to another person regarding what one is understanding when he is looking at an engineering drawing. So engineering drawing is of an object contains all the necessary information like actual shape, accurate sizes, manufacturing methods, etc., required for the construction of an object. So now, for example, sitting in a place, I make an engineering drawing and I simply send that particular drawing to another person who knows engineering drawing. Without me expressing any kind of verbal words, he'll be able to understand exactly what I'm trying to communicate. When I mean to say exact, all the true information which one perceived while I was making the engineering drawing, regardless of whether it is the shape of the object, size of the object, magnitude, material specification, etc., everything will be able to, the other person will be able to understand when he looks at the drawing. So therefore, engineering drawing is called as the universal language of engineers. Okay, so whether I'm sitting in India and if I communicate drawing to a person who is sitting in Germany, and if he knows drawing, he knows engineering drawing, he'll be able to understand exactly what I'm trying to communicate. So that is the beauty of engineering drawing. Now when we speak about engineering drawing, we are trying to capture the true information. So true information in all aspects we are trying to capture. So when we are trying to do this, we use a method called as the projections. Projection is something which is evidently seen when we capture a picture in a mobile phone, or when we go to a movie theater and when we are looking at a movie screen, there something is being projected onto the screen and we are able to see movie characters who are actual size is not visible on the screen. So therefore what I am trying to tell you is something which is projected onto the screen now appears to be in a false information, but nonetheless this is one of the important techniques that we have basically, which was invented by a person called as Gaspard Monge. He was a French scientist, mathematician, who introduced the concept, or basically invented the concept called as projections. As we've been discussing, Gaspard Monge basically invented the principle of projections. Principle of projection basically means that you are throwing forward the image of an object onto a screen. So therefore when you are able to use a source of light which passes through the object and falls onto the screen, the image of the object is captured on the screen. This particular principle is called as principle of projection. Now the problem that we have with the projection is that we need to formulate some or the other method wherein we will be able to capture the true shape of an object, whereas what happens in a movie theater is that the reel is in between the source of the light and the screen. Now the light source basically passes the monochromatic lights from through the reel that is being run, and as it moves on to the screen, what happens is the image of that particular object appears to be bigger. This problem is this method of projection is what is called as the finite projection, wherein we have a single source of light, and this is passing a number of monochromatic lights, rays of lights, and as it passes through this particular object, and by the time it reaches the screen, the shape and size of the object, the size of the object basically would have been bigger. So here, using this finite projection, we will not be able to capture the true shape of the object. So hence this cannot be used when we are trying to do engineering drawing. Whereas instead of having one light source at a finite distance, if we increase the number of light sources to infinite, okay, and we have the observer is at infinity, and the single rays of light which are all traveling parallel to the objects as depicted here in this particular picture, and they are all traveling perpendicular to the screen on which eventually the image is to be formulated. So I'll repeat once again, all the rays of light, infinite number of light sources, all passing single rays of light, and all of the rays of light, they're all traveling parallel to one another, and they're all traveling together perpendicular to the screen. When this kind of a projection happens, we will be able to capture the true size. The shape obviously will not change. The true shape, true size of the object will appear on the screen. This kind of a projection is called as orthographic projection. So just to tell the definition of orthographic projection, when the visual rays called the projectors are perpendicular, that is orthogonal to the plane of projection, the projected wave called as an orthographic wave, and the method is called as orthographic projections. Now when we are considering the orthographic projections, we will be able to capture the true size of an object. Now as depicted here in this particular picture, the light source is placed at a particular place, and in relation to the object, the screen is at the opposite end. The relationship between the observer, object, and the plane of projection is called as convention. So we will be requiring more than one such demonstration such as this to capture the shape of the object, size of the object in its wholesomeness. When I mean to say wholesomeness, here right now only one of the view is visible, that is only one face, that which is exposed to the observer, only that is visible right now. Whereas how is it visible from the top, how is it visible from the side, those information are missing in this particular drawing. So therefore we are going to introduce something called as weaves. So when I mean to say weaves, depending upon the relationship between the source of light, object and the observer. So when we change the position of the source of the light as well as the plane of the projection. So for example, if I have a light source here, there is an object here and there is a plane of projection here, we will be able to capture only the facing side of the object. When I change the position of the light source from this side to this side, automatically the orientation of the plane of projection also changes. So we are basically capturing weaves. So these are called as principal weaves. Okay, so if I consider that the object is stationary and there is a plane of projection, and if I am looking from the front of the object and projecting an orthographic view onto the plane of projection being standing vertically, the view that I am focusing on the vertical plane is called as the front view. So there is one view called as front view. The second one is when I change my orientation and keep the observer at the top, looking at the object which is stationary and projecting the image of the object orthographically as it appears on a horizontal plane. As it appears on a horizontal plane is called as the top view. And if these two views are not enough, then we will be imagining as if we are looking from the side of the object and we look at the object and project onto a plane of projection which is relatively available over there. We call those things as profile views. So these three views are called as the principal views, and correspondingly these views are projected on vertical plane, horizontal plane and profile planes. And these three are called as principal planes. So orthographic projection basically gives you different views called as principal views, which are respectively available on vertical plane, horizontal plane and profile plane, and these three planes are called as the principal planes. Now when we speak about vertical plane, horizontal plane and a profile plane, it looks like a floor of a house wherein you have a side wall, you have a bottom wall, you have the floor basically, and you have the wall on all the sides, lateral walls. You can imagine something like that. So if you imagine that there is a wall available, and if there is a wall available here in this as well, this is called as vertical plane represented as VP, and this is called as horizontal plane represented as HP. The intersection of vertical plane and horizontal plane, which are basically infinite in their own dimension, is called as the intersection of vertical plane and horizontal plane basically gives you the system of quadrants. This drawing basically represents system of quadrants. This is created by the intersection of vertical plane and horizontal plane. So before we move on to the to analyze the system of quadrants a bit more further, I would like to stress upon a fact called as a convention. So we use in drawing, we use something which is called as convention. Basically, convention is something which is universally followed without basically any kind of debate. So this was also given by Mr. Gaspard Monge in the 1800s, who invented the principle of projections. So convention basically speaks about relationship between observer, object and the plane of projection. For instance, when we are speaking about the system of quadrants, when we fix up a convention, that convention has to be retained to identify the quadrant, identify the weaves and identify the profile weaves also. So this convention has to be maintained consistently, regardless of whether we are doing the drawing in either of these places. Now when I speak about either of these places, this is called a system of quadrants. Now what we are going to do is, I am going to fix up the position of the observer in one of the horizontal planes. Obviously we cannot ask a person to stand on the vertical plane, so it is not possible. So we are going to make him rest on a horizontal plane. So when I fix this position, this is called as the observer. So regardless of whether we are dealing with something that is available here or here or here or here, the observer's position is basically fixed. So when I fix up the observer, if I have to explain what is in front of the object somewhere here, okay, we will be able to explain by saying, with respect to the observer, this particular colored area of the board is now above HP, in front of VP, towards the observer. So here it is called as above HP, in front of VP. So with respect to the observer, this colored area is now in front of the projection plane and in front of the vertical plane of projection and above the horizontal plane of projection. Similarly, if I imagine a colored chalk piece here, so this is behind VP, above HP. So when I am speaking about the colored area here, the observer position does not change, it is fixed. This system is what is called as convention. If I go to the third area here, this is behind VP and below HP, and similarly here it is in front of VP and below HP. So when we basically try to make a drawing, object could be here, here or here or here. So depending upon where the object is placed, as explained by the sentences or the words such as above HP, in front of VP, we say the object is available here. So when the object is available here, as explained by these two words, we call it as first quadrant. So first quadrant is when the object is explained as being above HP, in front of VP, we say it is in the first quadrant. Similarly, when the object is explained as being behind VP, above HP, we say it is the second quadrant. Similarly, when the object is explained as being behind VP and below HP, we say the object is in the third quadrant. And the last one is called as the So the intersection of vertical plane and the horizontal plane, along with the definition of the convention, basically gives you the relational explanation with respect to VP and HP, and this system of quadrant gives you the fourth quadrant. So first quadrant basically explained as the object being above HP, in front of VP. The second quadrant wherein the object is explained as being behind VP, above HP, and the third quadrant being explained as the object being behind VP, below HP, and in the fourth quadrant the object being explained as in front of VP and below HP. Now when we deal with the first quadrant, the principle of projection that we basically use is called as first angle projection. It's called as first angle. Similarly, when we deal with the second one, we call it as second angle projection. Third, similarly fourth. Okay, now when we deal with only the first quadrant, when we explain the object, somewhere here there is an object and the observer's position, obviously it is fixed. I am referring to the first quadrant right now. So when I say that this is the first quadrant and there is an object, now we are supposed to draw the views. So we basically start with the two principal views called as the front view and the top view. So front view is basically when the observer is available here, obviously it is fixed. Okay, he looks at the object orthographically and captures the picture somewhere here. This view obviously is called as the front view. He looks at the object from the top and this is called as the top view. So on the vertical plane you have the front view and on the horizontal plane you have the top view. Although observer's position is fixed here, we say that he is imagining as if he is looking from the top and is drawing the view that is he gets on the horizontal plane. I'll repeat once again, even though the observer's position, physical position is fixed, he is imagining as if he is looking from the top orthographically and is drawing this view, and this is called as the top view. Now we have a problem here. This system of quadrants is three-dimensional in nature. So as you can see here, it is three-dimensional in nature. Now when we want to draw this three-dimensional picture onto a two-dimensional sheet of paper, that is where the angle of projection, the principle of the angle of projection comes into the picture. Here what we say is vertical plane as it is can be represented on a two-dimensional sheet of paper. Now what I would need to do is that I want to tilt this horizontal plane in a particular direction so that both of this vertical plane and the horizontal plane are now appearing in the same plane. So what I mean to say is I want to tilt this horizontal plane by 90 degrees. Here also the tilting happens here 90 degrees. So the tilting happens here 90 degrees. So when it happens, both this vertical plane and the horizontal plane, they appear like this. This is the vertical plane and this is the horizontal plane, and the line which is separating the vertical plane and the horizontal plane, we basically name them as XY. So XY is the line of intersection, and the space above XY line in the first quadrant we say it is representing the vertical plane. The space below the XY line in the first quadrant we say it is representing the horizontal plane. So therefore the object, the picture available here, it appears here in the form of whatever the view that we got from the front view, and in the same line we draw the top view. So this is the front view and the top view. This conversion of a three-dimensional system into two-dimensional system is called as angle of projection. So what I demonstrated here right now is the first angle projection, wherein the vertical plane and the horizontal plane are separated by a line of intersection called as XY line. So as we have been discussing, I just demonstrated how we use the angle of projection principles when we are trying to make a picture or capture the waves, orthographic waves, which is the principal waves basically when the object is above HP in front of VP. Similarly, when the object is now available here, when it is available here, it's although observer's position is fixed here and these planes of projection themselves being transparent, what I say is the front view is available here, so therefore the front view will be visible here on this side of the plane and the top view will be available here. So when I need to represent this on a two-dimensional sheet of paper, I am tilting the horizontal plane as I discussed earlier in this particular direction. So therefore, when it goes like this, line of intersection called as XY, VP is already available above the XY line, and the HP, when I tilt it like this, even that also goes above XY line. So therefore, both the front view and the top view will be available above the XY line, and this is called as the second angle projection. Second angle projection. Okay. Similarly, when we are dealing with an object which is available here in this particular area, we have the vertical plane here and that appears to be below the XY line, and the horizontal plane is getting tilted above like this. It is going above. So it is capturing the view here, the top view, and it is going above. So therefore, HP will come here. So therefore, here the front view will appear below the XY line and the top view will appear above the XY line. As you can imagine, this is simply the reversal of the first angle. Whatever that we did in the first angle, that is being reversed here. In the first angle, we had the VP above the XY line and HP below the XY line, and similarly the waves were there. Whereas in the third angle, this is the third angle projection. We have the VP below the XY line, HP above the XY line, and the respective waves are available on those planes. Now similarly, when I am dealing with an object which is available here, its top view appears here and the front view appears here. So when I tilt the horizontal plane like this, XY line appears here, VP is already below the XY line, and HP is also getting tilted, so therefore HP also comes below. So therefore here both the front view and the top view appear to be below the XY line. As you can imagine, this is the reversal of the second angle. So this reversal, this tilting of the waves or tilting of the planes of projection which have captured the respective top waves, only the top views. We are not discussing about the front view. When I am tilting the top view, the plane on which the top view is captured, when I tilt this particular process is called as the angle of projection.